Hello everyone. So this sem you will be having differential equations 2 and real analysis 1. Those are the paper names for your fourth sem. Okay. So for you I'll be handling only Riemann integrals here. Okay. So under Riemann integrals topics are upper and lower sums, criterion for integrability, properties of Riemann integrals, integrability of continuous functions and monotonic functions, fundamental theorem of calculus, only the statement, problems, integration as a limit of sum, only problems you'll be having. Okay. Here is a glimpse at your lab syllabus. So these are the programs you'll be having in your lab this sem. So let's get into the first topic, that is partition of closed interval AB. Okay. So what is partition of closed interval AB? Let's see that. Consider an interval AB. Then a partition of AB is a finite set. So what do you mean by finite set? Which has finite number of elements in it. Okay. So now we can say for example, P is a partition and we are having the elements of P to be x0, x1, x2, etc. up to xn. So this is a set. This is a finite set. Okay. So now here I'll take x0 to be equal to A and xn to be equal to B. That means the first element and the last element. You know, closed interval means we will include these A and B elements also, right? Okay. So what is partition of A and B? It is nothing but a finite set. Okay. Partition of A and B is a finite set. So that is, we can divide this finite interval, finite and bounded interval into number of partitions. So that is, we can split this interval into number of partitions. Say for example, so you had this to be, say 0, 1 is the interval. So from 0 to 1 you have so many numbers in between, right? So I can make partitions. So 0, 1 by 2, 1 by 4, 0, 1 by 4, 1 by 2, 1 is a partition. Yes, that means I'm dividing 0, 0.1, 2, 3, 4. You can take any numbers between 0 and 1. So that becomes the partition of this interval. Okay. So now let's see. Here, yeah, we have to write these elements in such a way that x0 is less than x1, x1 is less than x2. That means we had an example, right? 0 and 1. That means we have to write in order. 0, 1 by 4 is least, then 1 by 2, then 1. Okay, accordingly. We have something called as sub-intervals. Sub-intervals is nothing but I can split this into small intervals. These, if I split this big interval into partition and if I take the small numbers here, I can make sub-intervals. That is x0, x1. If I put it into a closed interval, that becomes a sub-interval. Again, x1, x2 becomes an x sub-interval. Likewise, in between, if there is a element xr, I can take it to be x r minus 1, xr. That means we know it is 0, 1, 1, 2. That means previous number will be r minus 1, right? Likewise, we can write generally like this. Then xn is nothing but xn minus 1. Previous term will be xn minus 1. So it is xn minus 1, xn. Then we obtain the sub-intervals. The sub-intervals obtained by P will constitute a segment of partition P. Okay, now let's see what is length of this segment. Okay, we have segregated, that is segmented these intervals from the main interval, right? So length of these segments, that is the sub-intervals we are talking about. Okay, length of the segments IR. So this segment is this interval, length of this interval. How can you find this is using, we can subtract the greater number minus smaller number gives you the length. Okay, so see here, check this out. Length of the segment IR is equal to xr minus 1, xr. This segment is denoted by, we'll denote the length of the segment using delta r, and delta r is equal to xr minus 1 gives you the length. That is the greater number minus smaller number. Greater number was xr, you know that, right? So xr minus 1 gives you the length. The maximum number in such partition is called norm or mesh of P and is denoted by mod P and is defined by mod P is equal to maximum of this. That is, we are finding the length of each subintervals and making one more set. Okay, in that set, which is the maximum number, that is the greatest, highest number which you get here, will be the maximum, will be the norm or mesh of P. Let's see that with an example. Okay. So here we have an example. Check this out. We are taking an interval 0, 1. Okay, what is the partition of this interval now? The partition is 0, 1 by 3, 1 by 2, 1. I'll take the partition to be 0, 1 by 3, 1 by 2, 1. Okay, so now what is the subintervals from this? I can take it as 0, 1 by 3 to be one subinterval, and 1 by 3, 1 by 2 to be one more subinterval, 1 by 2, 1 to be one more subinterval. That is the maximum number of subintervals we can get from this. So after this, I am finding the length of the subinterval. What is the length of the subinterval? Denoted by delta, right? So since this is the first subinterval I1, I'll take it to be delta 1. Length of the first subinterval is equal to, how to find the length? Greater number minus smaller number. So we have 1 by 3 minus 0 is equal to 1 by 3. That is nothing but the length of the first interval. Now length of the second interval is denoted by delta 2, and likewise you're finding the length 1 by 2 minus 1 by 3 gives you 1 by 6. Again, length of this interval will be 1 minus 1 by 2. Now to find the norm or mesh, what is the thing? So you have found the length of these. So what is the, see, if you find the length of these, you can write norm of P can be written as maximum number obtained after finding the length. What are the lengths? We have 1 by 3, 1 by 6 and 1 by 2. So which is the greatest or maximum number? It is 1 by 2. So your norm of P is nothing but 1 by 2. Thank you.